Hello and good to see you. This is a session on underground excavation monitoring. In fact, we'll cover testing and probing during excavation, as well as monitoring of the excavation. During underground excavation, there are a number of activities associated with understanding the ground in order to improve the design and construction. Those activities include mapping and testing to gather more detailed information of the ground at the excavation location and depths, to verify and update the information obtained from earlier stage of site investigation. In grounds subject to uncertainties, for example, with suspected cavities and fault zones, probing is carried out to confirm those suspicions. The ground around excavation, the ground support elements, the excavation machines, and the adjacent environment that may be affected by the excavation are often monitored to ensure adequate support and minimum effects on the environment. We will cover a bit more detail on those activities. Mapping at excavation is primarily to map the joints at the excavated face and the sides after excavation and before being covered by shotcrete. At the excavated face, joint mapping can be done using compass and tape, photogrammetry, and digital techniques, similarly as in front of an outcrop rock face. We have covered joint mapping earlier in site investigation. With joint information such as joint sets, joint spacing, RKD, orientation, joint condition, weathering, and roughness, rock mass quality can be assessed. The actual rock mass quality may be quite different from the interpreted rock mass quality from earlier site investigation from a surface drain. Then we may need to modify excavation operation and the support design. The photo here is the excavation phase of an oil storage cavern at the sun 120 meters below the seabed. The earlier site investigation from surface would never be able to reveal that much details of the rock mass as shown here. With this new knowledge, excavation was modified accordingly. Groundwater inflow during excavation can be measured in order to assess groundwater condition. General groundwater condition can be assessed by observing seepages and the seepage locations to identify the seepage channels, for example, water conducting joints at excavation phases. If the inflow quantity and the rate is low, flow rate can be measured by or estimated by tipping bucket. If the inflow rate is high, then the inflow rate needs to be assessed by measuring water level increase in tunnel and the pumping out rate. Groundwater pressure can be measured by piezometers or sometimes estimated by flow rate. For deep underground excavation, measuring initial stress and deformability can be expensive during surface site investigation. Those measurements can be taken during excavation, with tests done from excavated tunnels. Typical tests are flat-jack tests done on roof and side walls to measure in situ stress in the surrounding rock mass and the rock mass deformation characteristics in tunnel roof and walls. In situ stress measurements by overcalling, on the other hand, is typically done by drilling from side walls. The stress measurements point are generally at distance, preferably more than 2D away, which is generally outside the zone of influence of the excavation. For example, overcalling point should be a distance of more than 16 meters from the wall if the tunnel diameter D is 8 meters. As the site investigations from the surface are often not able to provide sufficient details for grounds with suspected problematic features ahead of excavation, such as fault zones, cavities, boulders, water and gas, probing is the most effective way to check and to detect such features. Probing can be done by long-haul drilling, typically from excavation phase to probing ahead. Occasionally, if there is concern from sides, side probing from wall can be done, but the drilling length does not need to be long. Probing by geophysical exploration methods such as seismic, electrical, and electromagnetic are also nowadays available methods for front probing and side probing. Two methods can be used together or coupled. Typically use geophysical probing for fast scanning, and once anomalies are detected, drilling can be used to confirm. Modern excavations and drilling machines are equipped with sensors to monitor the machines, such as load, deformation, and vibration. The best example is data captured by tunnel boring machine. Typically, TBM records data on thrust force, rotation speed, rotation force, cut load, penetration rate, and vibration. Those data are usually used to assess TBM performance. However, those data can also be used to analyze rock mass properties, as machine data is induced from the response to the ground. For example, TBM thrust force, cut load, and the penetration rate are result from rock strength or hardness. Once such correlation is established, it is possible to use machine monitoring and the performance data to estimate rock mass and the ground properties and the conditions. Just as a good driller could tell whether the rock is strong or not from the thrust force, we needed to turn the information obtained by the excavating machine into knowledge on ground properties. We have mentioned about monitoring before when we are learning sequential excavation and the NATAM method. For NATAM, monitoring is a fundamental part of the excavation process. Underground excavation monitoring covers monitoring of tunnel convergence and the ground deformation, load on support, support integrity, surface settlement, and effects to the surrounding structures and environments. The table summarizes those monitoring activities and associated measurements and techniques. We'll explain in more details of those methods. Monitoring of tunnel convergence is to measure the decrease of opening size and the change in shape with time. Convergence can be measured by several pairs of points on the tunnel circumference. Geometrically, the measurements are in the form of triangles, as illustrated in the top figure. The distance between the 2 points are measured by using tape extensometer, shown in right. The method is simple, effective, and quick. Alternatively, we can use digital profile scanning method to scan the profile of the tunnel circumference. By processing the digital image, we can get the geometry of the profile and estimate the change. The images below is an example of tunnel profile scanning and the processed tunnel profile. Ground deformation is to measure the displacements of the surrounding rock mass using borehole extensometers. Borehole extensometer can be single measuring points or multiple measuring points in a single assembly. Common multi-point borehole extensometer, MPBX, are used, measuring the deformation of the rock mass at different distances from the tunnel roof and the wall, as shown as X1 to X5 in the drawing. In installing MPBX, boreholes are drilled on the wall or on roof into the surrounding rock mass. MPBX is inserted into the borehole and grouted. The displacements of the rock mass between the head and the each extensometer measuring point are measured. The measurements therefore gives the deformation of the rock mass between tunnel wall to the depths of the last measurement point of the MPBX. Occasionally, MPBX can also be installed from the surface to the deformation of the ground between surface and the tunnel roof, as shown in MPBX X0 in the drawing. Here is an example of measurements of multiple point borehole extensometer from the surface installed MPBX before excavation. X0 in the last slide. The excavation monitored is a large cavern of 30 meters span in granite. I did it because I wanted to get a complete picture of ground deformation before, at, and after excavation. If MPBX is installed from tunnel wall, we'll only catch the deformation days after excavation. In hard rock, much of the deformation would have already occurred. The measurement points are 2 meter, 6 meter, 12 meter, and 25 meters above the middle roof. Pilot and the slashing are heading excavation as shown by the insert joint at lower right corner. You can see the movement of the ground, particularly when heading is excavated. After heading is completed, the roof stabilizes and the benching does not cause roof to deform. The monitoring confirms the stability and provides the ground behavior during excavation. In addition to monitoring the ground, supports are also often monitored to check the loading and the stress condition. Support monitoring includes measuring stresses on the lining and in rock bolts by different stress and strain sensors. Stress on steel lining can be measured by load cell, as shown by the up photo. To measure stress in and on shotcrete and concrete lining, pressure cells are usually installed, as shown by the lower joint. Strain gauges can be attached to the steel reinforcement bar in concrete cage to monitor load on segmental lining. Effectiveness or performance of rock bolts can be monitored by measuring the stress or strain of the end-anchored bolts installed in the rock masses. Rock bolts can be instrumented by resistive foil strain gauges glued on the flattened bolt side or by vibrating wire strain gauge placed inside the bolt, as shown on the right. Additional monitoring can be done on bearing plates and the nuts using load cells. Tunnel lining damage and integrity is usually shown by cracking in concrete lining and water leaking. Monitoring includes visual inspection of cracking, measuring cracking widths using crack meter, and monitoring and measuring crack propagation and extension in concrete lining, as shown by the up figure. Detecting separation of shotcrete from rock using non-destructive testing methods, for example, using sonic wave measurements, as shown by the lower figure. Ground leakage through segment joints and cracks can be monitored through observation, measuring, and testing. In tunneling, particularly in urban area, ground surface settlement are constantly monitored. Monitoring of surface settlement above tunnel is usually done with traditional surveying techniques to measure any changes of ground elevation. For monitoring and assessing ground settlement and subsidence in large area, for example, associated with underground mining, particularly using longwall and the caving method, laser, radar, photo image, and digital image processing can be used to cover a wide area, as shown by the figure on the right. Ground surface settlement can cause surface structure movement and damage. Adjacent surface structures, settlement, and displacement can be measured by common survey method, or can be monitored by displacement instruments. Structure damage are mainly represented by cracking and are monitored by crack detection and measurements. For non-visible damage, non-destructive testing methods can be used. Underground excavation in rock can also induce hazards to people, building, and the environment. We can monitor vibration and noise induced by blasting and then machine excavation if excavation is close to houses and buildings. We sometimes need to monitor groundwater if it is affected by underground excavation by measuring water level, water quantity, quality, and the chemistry. Air quality internal and outside can be monitored by air quality monitor. Monitoring on effects of groundwater excavation on vegetation can be done through sampling, testing, and mapping. Monitoring technology has been progressing and developing. One of the major developments is the use of fiber optic strain sensors, also known as FBG, fiber Bragg grating sensors. With the fiber optic cable, we are able to perform long and continuous monitoring of the concrete lining around the whole circumference or along a long length. We have seen increasing use of remote sensing using flying drones and satellite to obtain ground profile, rock surface profile, rock mass information, and the joint distributions. Computing capability also helps digital image processing, particularly on 3D digital image coloration. The latest development is on machine learning. Through artificial intelligence and deep learning technology, we may be able to estimate ground behavior and to improve machine performance through data from the excavation machine. I'm finishing this session on underground excavation monitoring by showing the illustration here. You can take a close look on various instruments and the techniques used for tunnel excavation monitoring. Thank you for attending this session, and I'll see you later at the next session. Bye.